You knew it was coming. The song had to be here. What you didn't know was this hat existed. The fox hat. But on to this week's segment. This week's segment's on simple harmonic motions, like the sound a fox makes. So, what does the fox say was a viral video from a couple of years ago, but Elvis's masterpiece needs to be revisited every now and then. Plus, I have a hat, but I got one as big, and so we're gonna watch this. This is the song again, but it brings up a good point. I need to know from you, because you know better than I do, what the latest funny viral video song is, so I can put it in a video. So in addition to your comments at the bottom of this video, tell me what song should be in a video for next unit. In the meantime, we're going to talk about simple harmonic motion. It's an example of repeated energy transfers. So we're going to take the energy stuff we learned for the first part of this unit and put it together in an interesting way. Before we get too far into simple harmonic motion, we need to get some definitions down so we know what we're talking about. First, an oscillation. So for it to be simple harmonic oscillation, first it has to be oscillating. Oscillation just means something is repeating itself over and over again. So me just doing that was sort of oscillation. Something happens again and again and again. Periodic then further means that those oscillations happen at a regular interval. So it goes around once every second, it goes all the way around. So when we did the lasso, that was periodic motion, and we found the period of that, remember? But when we go one step further to simple harmonic motion, we get motion that's periodic, but that's not at the same force all the time. It's saying that the force is proportional to how far it's displaced. So like when we have a spring, as we pull our mass out further, the force gets bigger and bigger and bigger. So a mass spring oscillator is a really great example of a periodic motion, because I pull it out really far, I have a huge force out here. When it gets back to here, I have no force. When it goes over here, I have a large force. So big forces on the ends and no force in the middle is what gets us a nice periodic, simple harmonic motion. So just like with all of our different forces, is our energies, the total energy in a simple harmonic oscillator stays the same. So I could put a little T there, E total, and that's always the kinetic and the potential together. This is a little picture of what our simple harmonic oscillator looks like. It's a mass going back and forth and back and forth and back and forth. No friction, so that you don't lose any energy to non-conservative forces. Just going from kinetic energy in the middle to potential over here, back to kinetic, potential, kinetic, potential, kinetic, potential, over and over and over again. So our energy, potential energy, is going to be the spring stuff, and then we're going to have kinetic energy, and it's going to go back and forth between those two. When it's at the ends, we know it's all potential. We know it's in the middle, it's all kinetic, and anywhere in between, we can figure out based on what our x is or our v, whichever one they give us, how much of the energy is in each of them. The total doesn't change. So if you find one of them, you can always find the other one once you know what the total energy is. So this is an energy displacement graph for that spring situation we just had. Notice that the green total energy up here stays constant all the time. It's always up here at the top. So if we add the red and the blue at any point, they add together to get the green, and that's never different. But look at these two graphs. Notice they're both really quadratics, and we know that basically because 1/2 kx squared and 1/2 mv squared are my two equations. The squared part gives us quadratic. And they sort of go opposite each other. And so when we're in the middle, all of our energy is in kinetic. So it's the red stuff, and nothing is in blue. It's zero. When we're at the ends, all of our energy is in blue, and our red is zero. There is a point right here and there where the energy is split half and half. And because they're quadratic equations, it's not exactly halfway distance-wise. And one of the things you do a lot in these equations, in these things, is figure out where that point is. I'm going to leave that to your homework, but you know that you can figure that out. You know the total. You can say 1/2 mv squared plus 1/2 kx squared has to equal the total. You want them to be equal each other, and so you can figure that out. I think you can do that. Notice that maximum x also means maximum acceleration, because if my force is the greatest, my acceleration is going to be the greatest. And maximum kinetic energy also means maximum speed. And so sometimes they ask the question like, where is it going the fastest? And you have to remember kinetic energy is basically the same thing as speed. And so you can figure that out. It's going to be right there. Also, they use this word a lot, equilibrium position, so you know where it would stay if there wasn't any motion going on. Equilibrium is right that point right in there where the spring and the mass would stay if you just set them there. Let's do a quick example. So what we have is a spring up here, there's my spring, and it's got a 1 kilogram mass on it, and I pull it 0.5 meters this way, and then I let it go, and they want me to find what the velocity is, and I'm in the middle. So that's a pretty common simple harmonic motion problem. And basically that's just an energy problem. So this right here, well, first we make our 0 point, like we always do, and we notice it always stays at the 0 point, so we don't really have to put MGH in anything. We basically have ET here, ET prime, where's my prime? There's my prime, right here. And my ET is 1/2 kx squared, and my ET prime is 1/2 mv squared, and I just set them equal to each other. This one right here is going to be 1/2 times 100 times 0.5 squared. This one's going to be 1/2 times 1 times v squared. So I then say ET equals ET prime 1/2, get my calculator, 0.5 times 100 times 0.5 squared. That equals 12.5. That equals 1/2 v squared. That means that v squared is 25 and v equals 5 meters per second. Of course, things can be a little more complicated. So what sometimes they'll do is they'll say how fast is it going when it's gone halfway between where it starts and the equilibrium position, in which case this would be our ET prime. Now our ET would be the same, so we can just use the number we got from last time, but in our ET prime then would be have both 1/2 kx squared and 1/2 mv squared in it. And so we get halfway through the x would be 0.25 squared. And then I'd have to add 1/2 times the mass, which is 1, times the v squared, which is what I look for. But then I just take this whole thing here, set it equal to 12.5, and I can solve for my v squared. It's not really that much harder. It just adds one little bit of complication into the problem, but I think you can handle it. Last thing on mass spring systems is that since they're going back and forth at a steady rate, we sometimes want to know what that rate is. And there's an equation that tells us the period of a mass spring oscillator is 2 pi times the square root of the mass of the object divided by the constant of the spring. And while we're talking about that, we can say that the frequency is 1 over the period, so occasionally we want to know the frequency instead. We just find this and we take 1 over it. Notice something about this period. The nice thing about this period is that it doesn't matter what your x is. That canceled out of the equation. There's a derivation of this in your book if you want to do it, but really all we need to know for our test is that finding the period is this equation. Memorize it, be able to find that period. AP loves to ask questions about particular parts of the simple harmonic motion process, so you have to know that when we're up here is when our position, our S is what they like to use in AP, is way up at the top. Our velocity is 0 because it's not moving up there, and its acceleration is going to be back down towards the bottom. When we're at the unstretched point, the part where the weight would just hang there, the velocity is at a maximum. We have no acceleration there. It's all velocity, but then because our unstretched length is, our stretched length is 0, so x is 0, so F equals kx, no force. As we go farther down, my position is going to be down, my velocity is going to be 0 again, my acceleration this time is going to be back up this way. We get back to the unstretched length, x is 0 again, so there's no acceleration. My velocity is at a maximum because it's going to go through there, and it's going to go back and forth and back and forth. Now you notice if we start putting these together, this becomes a fairly familiar shape for us from our math days. It's sines and cosines. And since we generally start at our maximum compressions, so that'll be up here on the thing, we're going to call it a cosine. AP wanted to make a variable that would let you see that the cosine changed over time. And so they said A is going to be cosine omega t. Omega is a Greek letter. And it turns out that since the period is the time between maximums, then omega is going to be 2 pi divided by the period. So that when the period is 1, we have 2 pi t, and we get back to the same place we started at. And since frequency is 1 over period, the actual equation that AP puts on the formula sheet is that y equals a cosine 2 pi f t. The a is the maximum stretch, and the cosine tells us that we're going to start up at the maximum, we're going to go back and forth and back and forth. And it turns out that because there actually is a little bit of friction on our spring, we end up getting something that has sine cosine thing that gets smaller and smaller and smaller over time as we add something called damping. And damping just means that my amplitude is getting smaller and smaller and smaller over time. So you need to be able to recognize this as being that same cosine function. Actually, this is a sine one, but we want it to start as a cosine one. Getting smaller and smaller and smaller amplitude over time. So be able to recognize that as the vertical motion of the spring, or if we had a horizontal spring, it'd be the same thing. This could be x instead of y. While I did last week tell you the very best root beer in the world, maybe some of you are drinking it now, I have to admit, my beverage of choice out of all of them would be coffee. Pretty much the king of beverages. And I have to admit, I'm kind of a coffee snob. I don't like lots of different kinds of coffee. I go for the good stuff, and you should too. Or you should not drink coffee because you're still growing. Don't do it. If you do, get your own coffee. Grind it yourself. Not that Starbucks stuff. Get some good stuff. Now, I get my coffee from this guy that goes all around the world, finds the best coffee, sends me little letters about it, takes it back to California, grinds it the very day, roasts it, the very day that he roasts it, he sends it to me, I get it, this is the guy. Tonks coffee, it costs a little bit. It's kind of expensive, I'm not going to lie to you. I'm not going to tell you how much. If you're interested, go look at their website. They are wonderful. You will not be sorry that you ever had any of their coffee. And if you want to make good coffee, this is the system I suggest. It's called an AeroPress. It's really cheap, 30 bucks or so. You grind the coffee, and then you put it right in there. See where the things are? Yeah, right there. And you push down on the little plunger, and you create basically your own espresso. Really, really cheap, incredibly good. Anyone can do it. I make it every morning. It's amazing. And it was made by the same guy that did the Aerobi, that flying disc that goes forever. Like, genius man. Made the best Frisbee ever, and then decided, what else can I do? Let's make coffee better. Love that band. While I could do a whole video on coffee, I think that I'm going to have to do a little bit of physics, and to do that physics, we're going to talk about pendulums. So, in a pendulum, we again have two kinds of energy. This time we have mgh, as it comes from up here down to there. H is changing. That's turning into 1 squared this time, and so we get this basic equation there for the pendulum, which is a little different from the spring, which was spring to kinetic energy. But other than that, it's pretty much similar. We get a very similar period equation. You have to just memorize that basically, and that has to do with how simple harmonic motion works. We don't go too much into it in this class, but we go enough into it to know what the period is and to be able to do the different two energies and set them equal. If it was, halfway up between these two things, you'd know half the energy would be in kinetic and half of it would be in gravitational potential. And you get the exact same graph that you did in the other one, where you had the thing, then you had this one, and they equal the total up there. Same equation, just this time with two different kinds of energy, potential energy of gravity and 1 FmV squared. Every clock that we know is based on these particular period equations. Now it's nice because, like if you look at the wristwatch one, it doesn't matter what your x is to create the period. So as your x gets smaller and smaller and smaller, it's going back and forth and back and forth, smaller and smaller and smaller. You still have the same period. And so as it's springing back and forth, it keeps correct time the entire time. So that's why it's nice for clocks. And so this right here is the inside of a wristwatch, and there's a little spring, and it's a circular one that goes like round and round like that, but it goes back and forth and back and forth and back and forth, and that's what allows you to keep correct time. The same thing is true for grandfather's clock, and this one's the pendulum clock as opposed to the spring. You have the pendulum, it goes back and forth, and it doesn't matter what that theta is. As the theta gets smaller and smaller and smaller, it still keeps the exact same period, ooh, that was weird, as before, so it can keep correct time. You'll notice that all grandfather's clocks are about the same length, and that's because that's the length that gives you a second as the period. And you can calculate that. I think you'd do it in one of the quest problems tonight. Won't that be nice? Good luck. Okay, so I couldn't go an entire week without giving you some kind of a treat snack thing. My family and I went this Sunday to this Asian market. There's a picture of it right here. It's 10901 Lamar. This is the best place in the world. It's gigantic, has so many things that you've never seen before in your life. Go there some weekend. You will love it. My favorite snack that I got was this here. It's a coconut candy. It is so amazing. Incredible. My son's favorite was this little gummy thing. I don't like gummy things, but you should try that if you do. And this, under no circumstances, buy this chocolate. This is the worst chocolate I've had in my life. It was awful.